Welcome to the course on Introduction to Electrical Engineering. We will discuss today lecture 19, two port network part 2. To start with, we will discuss today the hybrid parameters, then the transmission line parameters, then different cascaded network, then of course, we will discuss some of the exercise and numerical problems, then followed by references. So, coming to the typically third set of parameter, which we call it hybrid parameters. This hybrid parameters is the combination of impedance and admittance parameters, which we already discussed in the last class, and these parameters of course are used many applications, like especially to typically do the computation of or analysis of transistors, amplifiers, which we will discuss of course maybe in the next few topics. So, here we have another set of parameters, which we define the voltage, input voltage, or let us say port 1 voltage and port 2 current, as a function of port 1 current and port 2 voltage, and of course, the matrix which comes like H11, H12, H22, H21, H22. Of course, in scalar form this is written like V1 equal to H11 I1 plus H12 V2, and I2 is H21 I1 plus H22 V2. Well, H parameters are commonly used in transistor modeling, and these hybrid parameters, the equation for hybrid parameters already we discussed it, like V1 I2 is a function of I1 V2 as in form of H11 H12 H21 H22, and where these parameters H11 is defined as V1 by I1, that is you can call it the input impedance, when the output port V2 equal to 0 means output port is second port is open circuited, and then H21 is the current gain I2 upon I1 when the output port again open. So, these are the two sets of parameters which you open, keeping the output parameters open or second port open, and then the third parameter H12 is V1 upon V2, that is voltage gain when the input, typically input port is open, means current in the input is 0, and then and then the H22 when I2 upon V2, then when the I1 is 0. So, these are the four parameters are defined in that manner, just to typically. So, how the representation is, to follow the popular model used to represent a particular variety of transistors, where you see V1 as a the current is drawing I1, and where K1 is the typically the input impedance, and K2 V2 is the typically a kind of voltage source, dependent voltage source coming out from the secondary side or second port, and on the secondary port we have V2 I2, and where we have a here in primary side we have a like a kind of Thevenin equivalent, and the second port we have a Norton equivalent. So, we have this another, you can call it the resistance or admittance K4, and in parallel we have a dependent current source called K3 V1, which is a current source dependent on input voltage. Like, so, this is a kind of ideal model which represent typically the transistor modeling, and we can write the following equation for here: V1 equal to A I1 plus B I2 B V2, and I2 equal to C I1 plus V2 D, where we can have this V1 equal to A I1 plus B V2 and I2 equal to C I1 plus V2 by D. So, we define another these four sets of parameter A, B, C, D, and we want to evaluate the H parameters from the above set of equation. So, we can say H11 is equal to V1 of I1, where V2 is 0 means the output terminal are shorted, and that is equal to K1, and H21 is the current gain I2 upon I1, where the output again terminal are shorted. So, that current I2 is flowing into it, that is equal to K3, and the H12 is the voltage gain V1 upon V2, where the current drawn from input port is 0, and the typically you can call it like a that is equal to K2, and H22 is the I2 upon V2, that is admittance, and where the current drawn from input port is 0. So, these last two parameters is means how your input current drawn is, typically there is no input source connected to here, and that is 1 upon K4. So, now you can say in terms of for reciprocal and symmetrical H parameter conditions, similar to other parameters, we say in terms of transmission parameters, a network is reciprocal if H12 equal to minus H21, and in terms of transmission parameter, a network is symmetrical if H11 H22 minus H12 into H21 equal to 1. So, now coming to the inverse hybrid parameters, or we call it G parameters, because that is H and here we call it the G. So, we can say this is again the G parameter defined here in terms of I1 V2 equal to is a function of V1 I2, and we call it these coefficient or functions, we call it G11, G12, G21 and G22, and of course, in scalar form these two, the matrix equation can be transformed to like I1 equal to G11 V1 plus G12 I2 and V2 equal to G21 V1 plus G22 I2, and G parameter is a alternative form of the hybrid representation. So, the G parameters can be found from the following form: G11 equal to I1 upon V1, where I2 equal to 0 means second port is open circuited, that is why the current is not in this, but there will be of course voltage induced in that, and that will be equal to 1 upon Z11. We already defined Z11 parameter, and that is equal to Y11 minus Y12 Y21 upon Y22 equal to H22 divided by delta H, where delta H is defined as H11 H22 minus H12 and H21, and similarly G21 define V2 upon V1, that is voltage gain when the I2 equal to 0 means the second port terminal are open, and that is defined in terms of impedance parameter Z21 upon Z11 equal to minus Y21 upon Y22 equal to minus H21 upon delta H. Similarly, GT2 is V2 upon I2, that is the, you can call it the impedance where the V1 equal to 0 means the input terminals are sorted equal to Z22 minus Z12 Z21 divided by Z11 equal to 1 upon Y22 equal to H11 upon delta H, and similarly G12 is defined as a current gain I1 upon I2, where V1 equal to 0 means the applied voltage, or you can call it input terminal are sorted, and but current I1 can flow into it, equal to minus Z12 upon Z11 equal to Y12 upon Y22 equal to minus H12 divided by delta H, and we have already defined where the delta H equal to N11 H11 into H22 minus H12 H22. So, now in terms of this inverse hybrid matter typically model, now it is just conversely opposite exactly the input terminals, we can call it a Thevenin equivalent. So, we call it like a V1 we applied, and you have a you can call it the conductance G11. In parallel we have a current source, dependent current source G12 I2 is coming from the secondary side current or second port current, and on the output side we have again V2 I2 flowing into the port, and G22 is again the resistance or conductance, and then we have a dependent voltage source G21 into V1, and that is virtually the voltage dependent voltage source coming from the input port. So, this is the model, inverse hybrid model. I mean, we have a hybrid model because it is a G is a just we consider as the inverse of H, like I mean. So, coming to now transmission parameters or transmission line parameter, or normally we call it ABCD parameters. So, these are also called T parameter, means transmission parameters, or ABCD parameters is another form of parameters related to the variables at the input port to those of at output port, and T parameters are also called transmission parameter because these parameters are useful in the analysis of transmission line, because they express sending end variables like V1 I1, and in terms of the receiving end variables like V2 I2, and the black box here that we want to replace the T parameters as shown here like a V1 I1, and you have a black box I mean where the output port or receiving port is like a V2 I2, and the equation for this we can write like V1 equal to A V2 minus B I2 and I1 equal to C V2 minus D I2. So, these are the we call it like a ABCD parameters of this two port network like, and this transmission parameter ABCD can be defined now in matrix form like V1 I1 is a function of V2 minus I2 ABCD I mean in matrix form, and we can say how we can find out A, that is voltage gain V1 upon V divided by V2, where I2 is 0 means output terminal are open, and C equal to I1 upon V2, where the I2 again 0 means output terminal are open, and this is you can call it the upper is the voltage gain, and this is the you can call it the kind of admittance, and B equal to V1 upon minus I2, that is, and where V2 equal to 0 means the output terminal are shorted, then only current I2 can flow, and D equal to I1 upon minus I2, that is current gain, where V2 again 0 means output current flowing into because of the short terminal at the output port of the this two port network. And in terms of now of course, we can call it what is the condition for reciprocal and symmetrical for the two port network in terms of T parameters. So, in terms of transmission parameters, a network is reciprocal if A d minus B is equal to 1, and in terms of transmission parameter, a network is symmetrical if A equal to D. Now, coming to inverse T parameters. So, when the terminal parameters V 1 I 1 of the transmission network expressed in terms of V 2 I 2, then network called the inverse T parameters, as you define again the variables here V 1 I 1 and V 2 I 2 as a 2 port parameters or variables. So, we can define now V 2 I 2 equal in function of as a function of V 1 minus I 1, and parameters we call it A dash, B dash, C dash and D dash, that is we call it inverse transmission parameters, and where we can define A dash equal to V 2 upon V 1, that voltage gain where I 1 is 0, it means the input terminals are open, and B dash equal to minus V 2 upon I 1, where V 1 again 0 means input terminal are shorted, and C dash equal to I 2 upon V 1, where the I 1 equal to 0, and D dash equal to minus I 2 upon I 1 current gain, where V 1 is 0 means the input terminal are shorted like. So, these are inverse transmission parameters. And now, coming to the generalized terminated 2 port network, I mean we can have here in typical application of 2 port network, the circuit driven at port 1 and loaded at port 2. So, figure shown here, it is that we are connecting ZL at the port 2, which is loaded, and we are applying the let us say the voltage at the port 1 with the internal impedance of the source ZG. So, ZG represents the internal impedance of the source, and VG represents the internal voltage of the source, and ZL represents the load impedance, and there are few characteristics of the terminated 2 port network, and some of them are like first is the input impedance, that we call ZI equal to V 1 upon I 1, output impedance Z 0 equal to V 2 divided by I 2, and current gain is I 2 upon I 1, and voltage gain we call it AB, that is V 2 upon V 1, and overall voltage gain we define AG, that is we call it V 2 upon VG. And here we call it like a typically the T network. So, we have a parameters of T network parameter we can define in T model, where we have a input voltage V 1 and output voltage V 2, and we have a parameter Z 1, Z 2 and Z 3, where the current is of input is I 1 and output current is I 2, and this we can represent in terms of this T model in the parameter Z parameters, that is now we can say what are these parameters here, what is Z 1, Z 1 equal to here Z 1 1 minus Z 1 2, and Z 2 2 is your Z 2 2 minus Z 2 1, and of course, this you can call it Z 3 Z 2 1 equal to Z 1 2 in 2 model, like in T network, and this from this model we can say we can get V 1 equal to as a function plus Z 1 plus Z 3 I 1 plus Z 3 I 2 equal to Z 1 1 I 1 plus Z 1 2 I 2, and V 2 is your Z 3 I 1 plus from the loop equation, that is Z 2 plus Z 3 I 2 equal to Z 2 1 I 1 plus Z 2 2 I 2. I mean from these two circuit we can define these two equation, and typically we can say comparing this with the Z model, we get the Z 1 1 equal to Z 1 plus Z 3, and we say Z 2 2 equal to Z 2 plus Z 3, and we say Z 1 2 Z 2 1 equal to Z 3. So, solving this equation for Z 1 Z 2 Z 3, we can say Z 1 equal to Z 1 1 minus Z 1 2, and Z 2 equal to Z 2 2 minus Z 2 1, and Z 3 equal to Z 1 2, Z 1 2 equal to Z 2 1. So, these are the kind of equivalent parameters represented in terms of that. Now, coming to pi network, which normally we represent in terms of this pi model in admittance parameters. So, where V 1 is the applied voltage and giving the current on input port, and output is the V 2 and I 2 port, and we have a parallel admittance like Y 1 Y 2 and Y 3, we call it pi model. And another pi model in terms of your admittance parameters, we say that where V 1 I 1 is the parameters here Y 1 1 plus Y 1 2 and Y 2 2 plus Y 2 2, and where the this your Y 3 equal to Y 1 2 equal to minus Y 1 2. So, now we putting this equation from these two model, how we can define this pi equivalent network model in terms of your admittance parameters of the 2 port network, which we already discussed. So, we can say from this pi model we can get I 1 equal to Y 1 V 1 plus Y 3 V 1 minus V 2 equal to Y 1 plus Y 3 V 1 minus Y 3 V 2, that is equal to Y 1 1 V 1 plus Y 1 2 V 2, and similarly I 2 is equal to Y 3 into V 2 minus V 1 plus Y 2 Y V 2, and that becomes in terms of V 1 V 2, that is minus Y 3 V 1 plus Y 2 plus Y 3 into V 2, and that is equal to V 2 1 V 1 plus y22 V2, and then comparing these two we can find out the parameters. This typically comparing it becomes like y11 equal to y1 plus y3, and y22 becomes y2 plus y3, and y12 becomes y21 equal to minus y3, and from this we can find out this pi network parameter y1, y2, y3 in terms of your admittance parameters. So, it becomes y1 equal to y11 plus y12, and y2 it is y22 plus y21, and y3 is minus y12 equal to minus y21. So, that is the relation between the admittance parameters and pi model parameters. And now coming to the typically as a cascade, an example as a with the cascade T network. So, one of the most important characteristic of the two port circuit or network with the T parameters is to determine the overall cascade parameters of the two port network, where we are connecting them in cascading. So, we have a V1 I1 with the T1 network, and the output is I minus I2 V2, and the second network of two port network which is fed by first network output is with the current V3 the current drawn I3, and then output is minus I4 and V4 with the T2 network. And we can have a what will the parameters of cascaded equivalent 2 network. So, we can say here that you can define V1 I1 as a T1 V2 minus I2 and V3 I3 equal to T2 into V4 minus I4, where V2 equal to V3 and minus I2 equal to I3 at the typically cascading of the two network. So, we can say V1 I1 equal to T1 into T2 as a function of V4 minus I4, and now we can find out this is the typically as a bridge network, I mean like that the equivalent path. So, we have here typically V1 I1 and we have a V2 I2 here, and we have impedance 4 impedance Z1, Z2, Z3 and Z4 of this bridge T network, and from this we can typically simplify this T network kind of equivalent, I mean how it is coming out typically as a two parameters, two network typically coming in typically parallel like N1 in parallel with the N2, and from this for N2 network you can say Z equal to Z1 plus Z2 Z3 and Z3 plus Z2 Z3. So, we can find out the bridge T network analysis parameters y11 admittance parameter Z2 plus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and y12 equal to minus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3. Similarly, y21 it is minus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and y22 minus Z1 plus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3. And from for this network 1 we say T equal to 1 Z4 0 1, and where we can find out y11 equal to 1 upon Z1 and y2 equal to minus 1 by Z4, and y2 1 equal to minus 1 upon Z4 and y22 equal to 1 by Z4. So, from these two now the combined you can call it equivalent y parameters of the bridge T network are from these two, that is y11 equivalent by cascading it is 1 by Z4 plus the Z2 plus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and y12 is again minus 1 upon Z4 minus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and y21 equivalent is minus 1 upon Z4 minus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and y22 equivalent is 1 by Z4 plus Z1 Z plus Z3 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3. That is a kind of you can call it the typically admittance parameters of bridge T network in terms of the impedance of that which are shown in the circuit like. Now, there are some quiz questions, short questions. I mean, what among the following represent the condition reciprocity of transmission parameters? So, that is AD minus BC, or the other condition AB minus BCD, and this all four. So, we say AD minus BC is the condition. So, another two port network is given where all three relations are given. The two port network is shown here. The parameter H21 is for this network is given. Typically, is that is your you can call it the H2 parameter is the gain that comes minus half. Similarly, you have like a two port network equation P1 equal to 50 I1 plus Z 10 I2 plus V2 equal to 30 I1 plus 20 I1, and which one of following parameter is 2 out of this. So, equal to 50 from transmission parameter. So, similarly, this is another question of which what is the condition in terms of for a two port network to be symmetrical, that is A equal to D, and for a two port network what is the condition for reciprocity, that is H12 equal to minus H21. So, now based on coming to solved numerical problems. So, we have here Numerical 1, find the H parameters of the circuit shown here, where we have a input with the 3 resistance with the output connected in kind of a star or T network, 2 ohm, 3 ohm and 6 ohm. To find H11 and H2, we sort the output terminal and connect a current source I1 to the input port as shown in the circuit. We can say V1 equal to I1, typically is coming in the your 2 ohm in series with the 3 and 6 parallel. So, it comes 4 I1 and H11 will become now V1 upon I1, that is equal to 4 ohm. Similarly, you can have a again connecting the voltage source at the output and keeping input open. So, from this you can find out minus typically I2 equal to 6 upon from previous circuit 6 by 6 3. So, I1 and 2 by 3 I1. So, H21 is I2 upon I1, that is minus 2 by 3. So, now obtaining the other two parameters to obtain S12 and S22, we open circuit the input port and connect the voltage source at the port output. So, we can say V1 will be now in term of this, typically the 6 divided by 6 by 6 plus 3, the current here multiply this into V2, that is 2 by V3, 2 by 3 V2, and H11 is nothing, H12 is nothing but V1 by V2, that is 2 by 3 from this equation. And now we can write in terms of V2 into I2 3 plus 6, and that is 9 I2. So, we can say H22 is the I2 by V2, that is 1 upon 9 Siemens. So, now coming to numerical problem 2, we have a network here, we have a current dependent source 4 I1, which is input current dependent source, and remaining parameters as a 1, 2, 1 and 2 ohm circuit here, and we can get H11 and H21 by considering the circuit here, considering that the output terminal are sorted. So, from considering the sorted, we can find out what is I1 here. The I1 will be like a V3, putting a nodal equation here, because current I1 is going here. So, V1 by 2, typically current going into this resistance, and V3 minus V4, virtually current going into by T. So, from this we can find out 2 I1 equal to taking 2 on that side. So, this will be your 2 V3 minus V4, and from this at node 2 we can say V3 minus V4 by 2 plus 4 I1 equal to V4 by 1, and from this we get 8 I1 equal to minus V3 3 V4, that becomes your 16 I1 minus 2 V3 plus 6 V4, and adding these two equations becomes 18 I1 equal to 5 V4. From this we got V4 equal to 3.6 I1, and V3 is your V3 V4 minus 8 I1, that is 2.8 I1. So, V1 becomes V3 plus I1, that is 3.8 I1, and that is why H11 now V1 I1 from this equation becomes 3.8 ohm, and I2 is your minus V4 by 1. So, that becomes minus 3.6 I1. So, here I22 becomes I2 upon I1 equal to minus 3.6, that is current gain. So, to get other two sets of parameter H22 and H12, refer to circuit B, where the input terminal are sorted, and we have a typical dependent current source can be connected by on the output. So, and where this 4 I1 will become equal to 0. So, from this we can find out from this V1 equal to in terms of V2, 2 upon 2 plus 2 plus 1 V2, and that is 2 by 5 V2, and from here H12 comes V1 by V2 equal to 0.4, and similarly I2 is V2 upon 2 plus 1, that is V2 upon 5, and H22 I2 upon V2, that is 1 upon 5, that is 0.2 Siemens. So, H parameters becomes now 38.4, minus 3.6 and 0.2, where these are typically voltage gain, current gain, admittance and impedance like. So, now numerical 3, find the ABCD parameters of the circuit, and where the network is given like a T network, 2 ohm, 4 ohm and 10 ohm, where V1, V2 are applied voltage and I1, I2 are current flowing into it. So, now keeping the typically the output terminal open, so I2 becomes 0. So, from which we can find out the typically the related to parameters of input. So, V2 equal to 10 I1. So, from which we can get the C parameters I1 upon V2, that is 0.1 Siemens, and here V1 is equal to your 2 I1 plus your V2. So, here it becomes V1 equal to 2 V2 upon 10 plus V2, that is 6 by 5 V2, and A parameters, that is V1 upon V2 equal to 1.2. And now keeping like your input open and output sorting, that is V2 equal to 0. So, we can find out now the relation between the other parameters. So, here the you can call it the typically we can say I2 equal to your 10 by minus 10 by 14 I1. So, D parameter is minus I1 on I2, that is 1.4, and the another equation is V1 equal to 2 I1 plus 10 I1 plus I2, or V1 equal to 12 I1 plus 10 I2 or V1 12 minus 14 by 10 from the previous equation. So, we can say I2 plus 10 I2 or we can call it B equal to minus V1 upon I2 equal to 6.8 ohm, and the combined parameters virtually comes here 1.2, 6.8, 0.1 and 1.4 as a T parameters of this T network or equivalent. Now, coming to determine the T parameters of the circuit shown here, where we have input terminal output terminal with the capacitance of minus J2 ohm and the resistance of 4 ohm between this. So, to find out T parameters here, so we can say output is let us say you are open applying the typically haircut I1. So, from this when I2 is open, output terminal voltage we can find out from this circuit. So, we can find out I1 and the drop across this. So, from this we can say V1 equal to 4 minus J2 I1 and V2 equal to 4 I2. So, we can find out A equal to your V1 upon V2, that is equal to 4 minus J2 by 4, that is 1 minus J 0.5, and the C parameter I1 upon V2, that is I1 upon 4 I1, it becomes 0.05, 0.25 Siemens. To determine the BD parameter, consider here the output terminal are shorted and applying the voltage. So, here in the 4 ohm resistor is shorted, so hence I2 equal to minus I1. So, DB parameter is your minus I1 upon I2 equal to 1 and V1 is minus J2 I1 equal to J2 I2, that is B minus V1 upon I2 equal to 2 J I2 upon I1, that is minus 2 J ohm, and hence ABCD parameter are 1 minus J 0.5 minus J2 0.25 and 1, which finally becomes typically the parameters, the Z network ABCD parameters. Like coming to numerical 5, determine the T parameters of the circuit shown here. We have here 1 ohm resistance, then T network of 1 ohm and 2 ohm, and with a current dependent source of current flowing into 2 ohm with the 4x. So, now to get the AC parameter, refer to the circuit here, keeping the outer terminal open where I2 is 0. So, in this circuit we can calculate what is at node 1 I1 equal to V0 upon by 2 plus V0 minus V2 upon 1. So, it gives you 2 I1 equal to 3 V0 minus 2 V2, and at node 2 V0 minus V2 divided by 1 equal to 4 Ix, and from here 4 V0 by 2, that is your 2 V0. So, it comes V0 equal to minus V2, and keeping the value from here we can keep 2 I1 equal to minus 5 I2. So, C parameters become I1 upon V2, that is minus 5 by 2, it becomes minus 2.5 Siemens, and I1 now getting the another parameter V1 minus V0 by 1, and this we can keep the value here V1 plus V2, or you can call it minus 2.5 V2 equal to V1 plus V2, or V1 equal to minus 3.5 V2, and this voltage gain A equal to V1 of A parameter V1 upon V2 equal to minus 3.5. Now, to get another set of parameters BD parameters, we short circuit output V2 equal to 0, and now we can find out from this circuit the parameters BD. So, at node 1 we say I1 equal to V0 by 2 plus V0 by 1, and it gives the 2 I1 equal to 3 V0, and node 2 it is I2 plus V0 by 1 plus 4 I2 equal to 0, and minus I2 equal to V0 plus 2 V0 equal to 0, or I2 equal to minus 3 V0, and from these we can have a 2 I1 plus I2 equal to 0, or I1 equal to 0.5 minus 0.5 I2, and D parameters come minus I1 upon I2 0.5, and I1 is V1 minus V0 by 2, that is V1 equal to I1 plus V0. Putting the value here, we say V1 equal to minus I2 upon by 2 plus minus I2 by 3, that becomes minus 5 by 6 into I2, and from which we can find out B equal to minus V1 upon I2 equal to 5 by 6, that is or 0.833 ohm, and the T network parameters are now here in matrix form minus 3.5, 0.883, minus 2.5 and minus 0.5. Now, there are some unsolved problem based on that. I mean, you can just solve it similarly for all these parameters. I mean, and well, these are the references from which we have developed this lecture, and thank you very much.